Hi everyone, this is video 6B of the Regents chemistry curriculum, and today you're going to be able to describe how valence electrons are transferred or shared between atoms by drawing simply just Lewis dot diagrams. So let's get started. Here are some questions. You should be able to answer these questions by the end of this video. The structure of NCl3, this should be a subscript 3. Same thing, this should be a subscript 4. Subscript 3. Okay, is trigonal pyramidal. You can read those. And if you can tell me whether these statements are true or false, now that's perfect. If not, please hold on tight. You'll be able to answer these questions and determine whether these statements are true or false by the end of this video. Okay. You can pause the video to see if you can answer all of them. Now I'm going to get started. All right, so Lewis dot diagrams. Before you draw a Lewis dot diagram, you must first ask yourself, what am I drawing a Lewis dot diagram of? Am I drawing a Lewis dot diagram of an atom? Am I drawing a Lewis dot diagram of an ion or a molecular compound? If you're drawing a Lewis dot diagram of an atom, all you need is a symbol and valence electrons. Here's an example. Draw the Lewis dot diagram of a sodium atom. The symbol for sodium is Na, and sodium has 1 valence electrons. You can look at the periodic table to confirm that. So here we are. Here's sodium. The symbol is Na, and it has only 1 valence electrons. If you don't know the symbol for sodium, that's fine. Just go to your reference tables and go all the way down to table S, and you will see the symbol and the name. All right. Going on, or going forward. Now, if you're drawing a Lewis dot diagram of an ion or an ionic compound, all you need to know is that you're going to have to follow the BVICS rule. If you're doing it for an ion alone, like let's say the metal ion, then all you need is brackets, the symbol, and the charge of the ion. So if I ask you to draw the Lewis dot diagram of a metal ion, we'll hang on to BVICS. BVICS is for ionic compounds. So if I ask you to draw the Lewis dot diagram of a metal ion, all you need is the symbol of that metal ion and the charge of that metal ion. So let's say sodium ion. The symbol of sodium is Na. The charge of sodium, according to the periodic table, is +1. Here it is. Periodic table, sodium has a charge of +1. Done. Moving on. If I ask you to draw the Lewis dot diagram of a non-metal ion, then here we have, for example, draw the Lewis dot diagram of a chlorine ion, then you still need the brackets, you still need the symbol, but now you're going to have 8 dots around the chlorine. Inside the brackets, you're going to have 8 dots, and it'll always be 8. Yes, always 8. And then you'll have the charge right on top. The charge, again, you get from the periodic table. Okay? So again, brackets, symbol, 8 dots for nonmetals, and the charge. Brackets, symbol, the charge. No dots for metals. Now, what are metals? What are nonmetals? Let's review again. Here's your periodic table. Here's your staircase. Right here. Okay, anything above and below the staircase, except aluminum and polonium, except Alpo, anything above and below, except Al and Po, is considered a metalloid. To the left side of the staircase, all of these elements are metals. To the right side of the staircase, all of these elements are nonmetals. Okay? So that's pretty much it. That's all you need to know. If you get a non-metal, put 8 dots, brackets, charge. If you get a metal, put no dots, brackets, charge. Okay, for ionic compounds, let's read this. Okay, so our objective was actually to be able to describe how the electrons were transferred from the metal to the non-metal. This happens in ionic compounds. So here are some examples. If you're combining calcium with chlorine, calcium has a charge according to the periodic table. Here's calcium. Calcium has a charge of +2. Okay? +2 charge means that calcium will lose those 2 valence electrons that it has. It likes to lose them because if it loses them, it will move to the second to last shell here and will have an octet, meaning a stable chemical electron configuration. And every element on the periodic table wants to achieve that chemical stability, with the exception of the noble gases right here, which are already stable, group 18. They don't need to gain or lose. They already have an octet. Or for helium, they already have a complete first electron shell. Since it only has one shell, it only needs that one shell to be complete to be stable. Okay, so calcium has 2 valence electrons and it wants to lose them to form a +2 charge. Okay, so going back to here. Here's your calcium giving away its 2 valence electrons to chlorine in the compound CaCl2. Now calcium cannot only bond with one chlorine, because if it bonds with one chlorine, calcium will be left with 1 electron. It will give one of its electrons to chlorine, but the other one, it cannot give it to this chlorine. Why? Because chlorine has 7 valence electrons and it's only willing to accept 1 more. One chlorine atom has 7 valence electrons, and it's only willing to accept only 1 more. So going back to the periodic table, I want to show you. Here's chlorine. Chlorine has only 7 valence electrons, and it would like to accept 1 more. Now you'll see many charges under that. Disregard those charges. These are very uncommon. The charge for nonmetals, the charge that's on top is the most common charge. That's what's most likely going to happen to chlorine. In other words, chlorine is going to have an additional electron to achieve chemical stability. You see this? 7 valence electrons it already has. If it gets 1 more additional electron, negative electrons are negative, so when you gain a negative charge, you gain an electron. So -1 means you're having an extra electron. You get 1 more electron here, chlorine will be chemically stable. Going back, calcium would like to bond with 2 chlorines. Calcium will bond with this chlorine, calcium will give its electron to this chlorine so that this chlorine will have a total of 8. Calcium will give its other electron to this chlorine so that this chlorine will have a total of 8 valence electrons. This chlorine will be happy with 8 valence electrons and will have chemical stability, an octet. This chlorine will also be happy with 8 valence electrons, will have a chemical stability which is an octet. And this calcium will always be happy because now it lost its 2 electrons and will have a chemical stability as well and an octet. Going back to here, when calcium loses those 2 electrons, now calcium will have an octet in the 3rd shell. All right, so that's how calcium bonds. Now, how do we draw the Lewis dot diagram of CaCl2? Very simple. Let's follow BVICS. So BVICS stands for B brackets. Put those brackets. Well, first of all, what is your compound? Your compound is calcium chloride. Okay? First, you need to know what the formula for calcium chloride is before we go into BVICS. What is the formula for calcium chloride? Ca is calcium, Cl is chlorine. Okay? Now this is not a formula, these are just symbols. The formula you'll get by crisscrossing charges. So calcium is +2, Cl is -1. Crisscross the charges, you will get Ca, Cl, but now the 1 from the calcium, not the negative or the positive. You don't crisscross negatives and positives. The 1 from the calcium is going to crisscross down to Ca, and the 2 from the, the 1 from the chlorine will crisscross down to the Ca, the calcium, and the 2 from the calcium will crisscross down to the Cl. So what you're going to get is this compound formula. Ca1, Cl2. Okay? That means you need 2 chlorine atoms to combine with 1 calcium atom. So, you can organize this in a nice igloo. Here's a nice igloo. We're going to write the name on top. We're going to call this the calcium chloride igloo. We're going to give that igloo some windows. Here I'm going to have the ion formula, also known as the charges formula. Here I'm going to have the compound formula. Okay, the charges for calcium, Ca is +2. For chlorine, Cl is -1. And the compound formula, I get it when I crisscross those charges. Again, you crisscross the magnitudes, you don't crisscross the negative sign or the positive sign. So I'm going to have Ca1, Cl2. Okay, so now I have calcium chloride. Now that I have the ion formula, the I, and the compound formula, the C, I have my I and C already from the BVICS. Now all I need to do is apply BVICS. Now what does B stand for? B stands for brackets. Here's a bracket for the calcium symbol, B for brackets, S for symbol. Now here's a bracket for the chlorine symbol. Okay? Now V. V stands for valence electrons. We know that only the nonmetal gets valence electrons, and it gets 8. So here's the nonmetal, chlorine. It's on the right side of the staircase. It's going to get 8. Here are 8 dots that represent the valence electrons of chlorine. Now, I stands for the ion formula, which is the ionic charges. You already got them. Calcium gets a +2. Chlorine gets a -1. Now C. C stands for the compound formula, which is the subscripts are going to turn into coefficients. So you can either say that you have 2 chlorines and 1 calcium, just like it shows here, or you can say that you have 1 calcium and 2 chlorines. Both of these are acceptable. Another acceptable way to actually draw this would be a calcium with a +2 charge, and then chlorine, -1, 1, 2, 3, 4, 5, 6, 7, 8, and another chlorine, -1, 1, 2, 3, 4, 5, 6, 7, 8. All of these are ways for you to actually draw the Lewis dot diagram of calcium chloride. All right, so again, B for brackets, V for valence electrons for the nonmetal, I for the ionic charges. Just copy them and paste them from here onto the Lewis dot diagram. So this is your Lewis dot diagram right here. And then the C is the compound formula, which tells you how many atoms you have. You can either use coefficients to represent those numbers of atoms or put them as subscripts, or you can just draw how many atoms you have altogether. So you'll do this, or you'll follow this method whenever you're drawing a Lewis dot diagram of an ionic compound. Of an ionic compound. Okay, now for drawing Lewis dot diagrams of molecular compounds, or compounds that are made of nonmetals only. So molecular compounds are made of nonmetals only. There's no metal in there. So you don't use BVICS if there's no metal. What you're going to do, let's read a little bit. these compounds are made of nonmetals only. Keep in mind that hydrogen will always only bond once. Or hydrogen will always bond only once. Single bond means a pair of electrons. So when you have a bond between, let's say, hydrogen and F, this means that one of the electrons came from F, the other electron came from hydrogen. You never want to draw a bond like that. You either put the dots like this, or put the bond like this. You never want to have a bond, dots and a line at the same time. That's wrong. But I just drew it like this for demonstration purposes, so you know that the bond is kind of like a bridge between the electrons from fluorine and the electron from hydrogen, in this case. Okay, going on further. Keep in mind that in a covalent bond, which takes place in molecular compound, electrons are shared, unlike in ionic compounds where electrons are transferred. Like in the previous case here, the calcium electron was transferred to chlorine. The calcium electron was transferred to chlorine. Okay? Okay, so now let's try some examples. Here, you can I'm gonna do these and you can read about them later. Okay, I'm gonna do these three: NH3, CCl4, and HCl. So here, NH3, CCl4, and HCl. I'll also do H2O as well. Okay, let's start with H2O. H2O is a bent structure, meaning it's the most common bent structure. So H2O, there are two H's and one O. So here's an H, here's another H, and here's the O. Now, valence electrons are very important when it comes to drawing Lewis dot diagram of molecular compounds. So oxygen, according to the reference table, or according to the periodic table, we see oxygen has a total of 6 valence electrons. Okay? Now, since oxygen has 6 valence electrons, it wants 2 more. If it sees hydrogen, what's it going to do? It's going to try to work out a deal with hydrogen. I'll give you access to my electrons if you give me access to yours. So oxygen has 6 valence electrons. 2 of those 6 electrons will face hydrogen and try to negotiate a deal with it, while the other 4 will kind of stay up here, facing away. Now hydrogen, it only has 1 valence electron. You can look over here, you'll see that hydrogen only has a single valence electron. Hydrogen is not stable with a single valence electron. It wants 1 more to achieve chemical stability. In other words, it wants this single shell of electrons that it has to be complete with 2 valence electrons. The first shell is complete with only 2 valence electrons. So it wants to achieve chemical stability by having access to an extra electron. Okay? So hydrogen is also willing to work out a deal. So it'll have one of its that 1 electron that it has facing the oxygen, and that same thing, this other hydrogen is going to do the same thing. That 1 electron that it has is going to face the hydrogen. This is your Lewis dot diagram for a molecule for water. That's all you need to do. Now, if you want to write this with bonds, then this is what you're going to do. You're going to do the same thing. The oxygen, the 4 valence electrons are hanging here. And then you want to represent these 2 electrons with a bond. So you're going to say bonds with hydrogen here, bonds with hydrogen here. Done. Now this is H2O. Important thing to notice here, you don't want these 2 dots to be too far away from each other, those dots, you don't want to draw this like this. You never want to draw this like this, where you have the oxygen valence electrons, a total of 6, and then you have the hydrogen here and the hydrogen here. Then people are gonna get lost. Like, why is this so far away? You want to bring them as close as possible. So you want to kind of actually like do it like this, so to show that they're going to be bonding. All right, so that's it for water. Now let's go on and talk about NH3. NH3 is 4 atoms, and according to what we just read, 4 atoms would have a trigonal pyramidal structure, where 1 atom's in the middle and 3 other atoms are surrounding it. Hence why tri. Tri means 3 atoms are surrounding a central atom. So in this case, I only have 1 nitrogen, but I have 3 hydrogens, so the nitrogen is going to go in the middle, and the 3 hydrogens are going to go around in a trigonal pyramidal structure. So H, H, H. Nitrogen has 5 valence electrons. It is not happy with 5. It wants 8. So instead of having all 5 valence electrons face the hydrogen and ask for to share 3 electrons, what it's going to do is that it's going to have only 3 of its valence electrons. Again, nitrogen has 5 valence electrons. It's going to have 3 of its valence electrons exposed to the hydrogen, and then the other 2 will face away from the hydrogen. You still have to include all 5, but you're only going to have 3 of them facing the hydrogen, and then the hydrogens, and then the other 2 will kind of face away. So here are the 3 valence electrons. This one will face that hydrogen here. This one will face this hydrogen here. This one will face this hydrogen here. This hydrogen and this hydrogen. And then the other 2 electrons will not face other hydrogens. So they'll kind of just like hanging over here. Okay? So with that said, now we're done with the nitrogens. Let's deal with the hydrogens. Hydrogen only has 1 valence electrons. Hydrogen has a single valence electron. So that single valence electron for hydrogen is going to face that single electron for nitrogen. This one faces this one. Same thing for hydrogen. This one faces this one. And then hydrogen again here. This one faces this one. That's pretty much it for nitrogen trihydride, or also known as ammonia. You can rewrite this or redraw this like this. NH3. Don't forget the electrons for nitrogen that did not bond. Okay. Now the next one we're going to do is CCl4. Here's CCl4. This is a 5 atoms, so it's going to follow tetrahedral structure, which 1 carbon is in the middle, and then chlorines, 4 chlorines, tetra for 4 chlorines are going to be surrounding the carbon. So carbon has 4 valence electrons. All 4 of those carbon electrons need to bond to other atoms, all 4 of them, because carbon needs 4 more. So it's going to have all 4 of those valence electrons exposed to the other atoms so that it can try to work out a deal and actually have access to more electrons. So here's the first carbon atom, first carbon electron that's going to face the chlorine, second carbon electron, third, and fourth. Chlorine has 7 valence electrons, so it needs access to 1 more. So one of the chlorine's electrons is going to face the carbon electron, and that's what's going to happen. So here we have the 7th, and then the other 6 are going to face away. So here's the chlorine 7th electron is going to face this electron. So this one would face this one. So again, chlorine has 7, so this is one of them. The second one, the third, the fourth, the fifth, the 6th, and the 7th are going to face away. Same thing here. Chlorine has 7 valence electrons. One of them will face that carbon's electron, and then the second, the third, fourth, fifth, sixth, 7th face away. Same thing. Same thing. Okay, that's pretty much it for carbon tetrachloride. If you want to redraw this, you can simply just connect the dots. So this would look like this. C, Cl, 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 and then you'll have your dots here. Next, we have HCl. So for HCl, I'm going to draw it right here. H has 1 valence electron. Cl has 7. One will bond, the other will hang here. So it would look like this. HCl. Okay. And for CO2, sometimes some electrons will actually, some atoms will form a double or a triple bond. Let me show you an example of that. For example, CO2. In CO2, here's CO2. CO2 is also a linear structure. C goes in the middle, oxygen here, oxygen here. So carbon has 4 valence electrons. All 4 need to be bonded. So this 2 will bond with the oxygen on this side. The other 2 will bond with the oxygen on that side. Oxygen has 6 valence electrons. It needs access to 2 more. So 2 of the 6 valence electrons that it has will face the carbon, while the other 4 face away. Same thing here. And now this is carbon dioxide. You can obviously redraw it like this. For nitrogen molecule, so here's N, or diatomic element nitrogen, otherwise sometimes called a nitrogen molecule, you actually may have a triple bond. Nitrogen has 5 valence electrons, so here are 2 nitrogens. Nitrogen has 5 valence electrons. It needs access to 3 more. So, notice my wordings, 3 of the valence electrons that it has will face the other nitrogen. So, 1, 2, 3 will face this nitrogen, while the other 2 will face away. Same thing here. 1, 2, 3 will face this nitrogen, while the other 2 face away. So you can redraw this like this, and that would be your nitrogen molecule. Ladies and gentlemen, this is pretty much it for drawing Lewis dot diagrams. Let's go back to your questions. Read those questions, determine whether the following statements are true or false, and answer the questions. All right, thank you.